So hello, everyone. Thank you for joining us for this August edition of the 2022 GLASE webinar series. We will be having a roundtable today headed by representatives from 5 different lighting manufacturing companies, all of which are industry members at GLASE, the Greenhouse Lighting and Systems Engineering Consortium. My name is Haley Rylander. I'm the Extension Specialist with GLASE. And before we start our webinar today, I would, as always, like to extend a huge thanks to our current GLASE industry and CEA members for their support. It's because of them that we can promote activities like this and have them free and open to the public to support a wide audience. Today's webinar is sponsored by a GLASE member and one of our panelists today, Sollum Technologies. So let's take a minute and learn more about their company before we get started with our roundtable. Great, thank you so much, Sollum, for your support, and you'll get to hear a lot more from them during our panel today. There we go. I would also like to draw everyone's attention to an early save the date shout out. GLASE is going to be having our first annual summit in person since COVID started, which is really exciting. So that is going to be happening in early to mid-November. We're still nailing down an exact date, but be sure to mark your calendars, and that's going to be in person at Cornell University in Ithaca, New York. And we should have a lot more details on that coming out in the next week or so. So let's get started with our roundtable now. I am going to let our hosts for this introduce ourselves, and then we will allow our panelists to introduce themselves one at a time. So I've already introduced myself. Let's go on to Neil Matson.
Good day, everyone. I'm Neil Matson. I'm the director of the Controlled Environment Agriculture Group at Cornell University, and I'm a horticulturalist. So we just started our fall semester at Cornell, and I'm teaching a hydroponics class.
Hi, hello everyone. My name is Erico Matos. I'm the Executive Director of the Greenhouse Lighting and Systems Engineering Consortium. And I'm very excited to have this roundtable with some of our GLASE members today.
Great. Let's move on to our panelists and let them introduce themselves. So first, let's go in order of my screen with Woody Smith.
Hi, my name is Woody Smith. I'm the Chief Technology Officer at Vertaag. Vertaag basically started as a lighting company 25 years ago under a different name. It's been around for a long time, LED lighting over the past 10 to 12 years. And we've developed complete systems for lighting interfaces, software, firmware, the whole bit. But lighting has always been one of the really key elements, so we put a lot of emphasis in that area.
Thank you. Louis Brun.
Thank you very much. So Louis Brun, I'm a CEO co-founder of Sollum Technologies. Very proud to be here and be a contributor to this exciting organization, as there's we foresee a revolution coming in lighting with the emergence of LED, and we certainly see ourselves as playing a central role with our dynamic lighting solution that has been demonstrated its benefits in the past years and moving forward. Thank you very much.
Thank you. Brian Harris.
Hey everybody, Brian Harris. I am the technical sales rep for the Eastern US for Hort Americas. Hort Americas is a controlled environment ag company specializing in LED lighting, engineered substrates, and hydroponic fertilizers. And we're also the exclusive distributor for North America for all of current, that's previously GE's horticultural lighting.
Great. Colin Bryce.
Hello, I'm Colin. Great to be here. I work with Signify, and we were recently named Philips Lighting, but since have renamed and have really been synonymous, our company, with lighting over 100 years. And over the last 15 years, really delving and working predominantly with our team in the horticultural space. And so I work with the North America team. I'm a sales application specialist or plant specialist. So we're where the horticulture meets the practice on the grower side. So we work mostly with our customers to make the most out of the systems they invest in. And great to be here. Hope to be able to share some of what I've been able to learn on the road and with our end users over the last few years.
Thank you.
Thank you.
And Sanaz Masjid.
Hi everyone, I'm Sanaz Jara Masjid. I am a PhD agricultural engineer. I work at Agnetix, LED lighting company, as Director of Biological and Machine Vision Systems. I work with sensors and data and images and analyzing them. That's something that Agnetix as the LED lighting company promotes, that lighting comes with control. I'm very glad to be here, and I'm sure that there will be a lot of learning for me as well here.
Great, thank you, everyone. So let's get started. We have a list of questions that we've compiled. We had all of our registrants for this webinar gave them the ability to submit questions as they registered. So from those that we had submitted, we've come up with a list of questions that we're going to allow to just guide the conversation and get some good information from these awesome panelists. So let's start with Neil Matson for the first question.
That's great. Thank you, Haley. This is a perennial question that I also get from growers. How important is lighting spectrum as opposed to lighting intensity for crop production and development? And I'll give each of you a chance to answer. You might think about the environment that they're growing. So like, is it indoor sole source lighting or greenhouse supplemental lighting, as well as like yield and plant quality types of things. So how important is spectrum versus intensity? And Sollum, could I ask you to go first? Or Sanaz, sorry.
Oh yeah.
From Sollum.
Of course, certainly. A spectrum of light is important. In my experience in the studies that I follow, spectrum is very important, especially if you're looking into indoor agriculture versus greenhouse growing. So we all know that we are trying to copy what sun is providing to our plants, and in indoor settings we want this full spectrum PAR light plus near infrared, which recent studies are saying that we need to provide far red for our plants as well. Plants need that. Plants utilize that. But how much of each region of the electromagnetic spectrum are they using or they require? So this is the most important question. And based on the studies, this is different. If it's red region or blue region, this is very different in plants, or green region. We know that we need this this entire PAR region, but how much of each is basically providing us the lighting spectrum which is needed. So in greenhouse settings, we are getting this region from the sunlight, but we need to provide the spectrum that they need the most and they require the most. And if we provide it for them, they will thrive better. So I think the question comes down to this, and it's important for us to know how much of each section of this spectrum is important for plants and provide that. But in the question, when we are comparing this to lighting intensity, is it a comparison? I don't think we should compare that. But when we come up with the correct spectrum for plants, we need to provide more intensity based on the plants. We know plants have a limit of how much they can take this light. But I think traditionally we focus on how much light our plants or our leaf can get. Like especially in the studies, I can see that we are looking into details of leaf, but the thing is that we need to look at it at canopy level. In canopy level, things can be different. But yeah, generally that's what I think about the spectrum versus light intensity.
Thanks for letting me put you on the spot, Sanaz. Now we'll go to Sollum and Lewis. Would you let us know your thoughts?
Well, I definitely agree with the importance of spectrum and light spectrum. We've seen that in many different cases where the different mix and the impact of different wavelengths can have on stem elongation, for instance, and that would even vary within a similar crop, like peppers, for instance. Like Urix will not necessarily behave the same way as Ginas and stuff like that. Similarly with leaf size, or try to play with the spectrum and let the grower control then foliage overlap and root development. So these are all aspects that are, I think the intensity is something that is pretty well understood today. And time is now to move the focus on understanding truly how the different wavelengths do impact. We've seen the impact of far red, for instance, on stem elongation but we foresee a lot of different aspects that will move forward and that will have impact also on the morphology, but also crop quality and shelf life once it's harvested. So it has to be taken into account. And especially with greenhouse supplemental lighting, the light is not the same everywhere in the world. There's a lot of tremendous input that are coming from Holland, for instance, but Holland is at the 51° north compared to Columbus, Ohio, which is at 39, which is like over 1,000 kilometers, almost 1,000 miles. So all these aspects show that intensity is playing a big role, but as we go, spectrum quality we foresee playing it even a further role in that aspect.
That's great. Thank you. Brian, your thoughts?
Yeah, so my position is really that in a greenhouse setting, supplemental lighting is just that, supplemental lighting. The sun is providing a majority of the full spectrum light that we're needing. So adding photons is the most important aspect of that. And so spectrum is less important when it comes to a greenhouse lighting. Now, obviously, there are situations where we can steer a particular morphology in a plant if we're wanting to as he said, extend the internode spacing with far red. A lot of that, though, is still being supplied by the sun. If we look at turning lights off at the end of the day and allowing that natural far red to come in, impact the plants, it comes down to, are we providing the DLI that the plants need in a greenhouse more than anything else? And so photons are the key to that, whether it's red, blue, green, how we divide that up can have impacts. There's situations with lettuce where we have a glazing that reduces the blue content of the light. And so by adding a high blue light at the end of the crop cycle to increase the red morphology on those plants can be beneficial. So there's specific situations where spectrum does become important, but they're very specific. And so in general, it's more important to focus on the amount of photons that we're providing and balancing the DLI that crop needs from our standpoint. Now, as we look at indoor sole source lighting, that spectrum does become much more important. If we're looking at strawberries, we require some far red to get that stem to extend out. We're not going to have, good fruit production if we don't have far red in the spectrum. Same thing for, some head varieties of lettuce. They don't do as well with a high red or a high blue. They need that lower blue ratio to form the crop properly. So it's much more important in a sole source lighting than it is in a greenhouse setting. So.
Thank you, Brian. Woody, do you want to go next?
Sure. One of the things that we run into pretty frequently that ties into this with a lot of growers is energy consumption, as well as optimizing the growth period, right? So one of the reasons we jump into the whole LED thing is that if you look at the spectrum of, photosynthetic action in a plant, there's basically 5 different wavelengths of light, 5 different regions of wavelengths that we need to reproduce. My background is just tons and tons of experience with very high power metal halides, high pressure sodium, stuff like that. And that's all great, but when you look at the spectrum and how much energy is being produced, very little of it typically is photosynthetic. So you might go in there with just a PAR meter and go, hey, this is fantastic. We've got all this energy. But when you come back and you filter it, like we make these remote sensors that have filters at the specific photosynthetic frequencies, the amount of energy in versus the amount of energy for photosynthesis is hugely disproportionate, right? So using an LED that is able to produce energy at those specific photosynthetic points is far, far more efficient. And that's becoming one of the big issues for a controlled environment where you're in a enclosed space. But we also use those sensors so that during the course of daytime, we can actually monitor, what is the spectrum of lighting, because it changes over the course of the day. It's not constant by any means. It changes both in spectrum and in intensity. So using sensors, we can basically determine really what's going on. And at that point, we can augment natural sunlight at different times of the day to get better photosynthesis, to achieve higher levels of photosynthesis. And that relates directly to energy consumption. So if you took a 2,000 watt metal halide and look at it, fantastic light, but a small percentage of that is actually photosynthetic. You've got a huge amount of infrared, you've got a huge amount of ultraviolet coming out of the things, an awful lot of green spectrum, which doesn't do a whole lot for most plants. But you're putting in enormous amounts of power and generating a huge amount of heat, which then translates to your air conditioning bills and everything else associated with it. So that's kind of the direction we look at, where spectrum is really the most critical thing, and achieving the optimized spectrum at different stages of plant growth. It will change over the plant's life cycle. And we basically pretty much know what that characteristic is. We'll emulate that over time, and then we'll also use light sensing in open growing conditions to figure out what the spectrum of natural light is, and then how to augment that. The other thing that allows us to do is extend the growth period. So knowing what spectrum of light it is that's optimum for a given plant, we can extend the number of hours in the day and achieve extended growth cycles. So for that reason, spectrum to us is far more important than just sheer intensity.
Thank you. Yeah, that's great. Last but not least, Colin.
Well, I couldn't agree more with, several of the points that were made, and there's too many to list, but one point that Woody brought up that I'd like to touch on as well is the energy efficiency factor. Directly to your question, Neil, when it comes to intensity versus spectrum, greenhouse versus sole source, the way that we approach it as a group and the way that I look at it personally is that as we start to increase the proportion of total light provided by an artificial lighting system, it sounds like we all agree on this call that as you increase the fraction from 0 to 100% and it becomes sole source, the spectrum plays a more and more dominant role in the outcome of that crop. By and large, in most cases, including sole source cases, the yield outcomes or the predicted biomass accumulation rates, we can pretty well center our focus on the DLI, or the daily light integral, which is just that function of intensity over time, given that that light is within the PAR range, or the 400 to 700 nanometer range. Typically, we see a 1-to-1 yield achievement on a same ppfd or same mole sum basis, given two different spectral types. So we tend to parse out spectral recipe when it comes to yield outcomes, given that we're talking about spectral compositions within the PAR range. And if we start throwing UV or far red in, there becomes a much more convoluted question that we tend to avoid going into greenhouses with what we look at as non-electrically efficient spectra. So if we go in with something that has a very low component of a deep red 660 nanometer chip in the module, we tend to steer towards more energy efficient applications when we can, just because the operating expense of a luminaire will be completely determined by its efficacy. And if you measure the same PAR value for a luminaire with an efficacy of 2.7 micromoles per joule versus one with a slightly higher, you'll start to see a proportional reduction or increase in energy consumption for that lighting system. So we always try to balance energy savings, crop yield, and then needed secondary morphological outcomes. So if a grower needs more expansion out of a butterhead crop, we would recommend inserting 5 to 10% of far red in that supplemental light spectrum, because to that grower, that increased cost and reduced efficacy made sense. So we tend to try to mutually exclusively offer those secondary spectral benefits only when they make sense for the increased cost, which they tend to if we look at increased blue fractions to get better coloration, applying far red to everbearer strawberries to get the trusses long enough. Almost always when we steer away from the most energy efficient spectrum, we're coming to some cost in a greenhouse specifically. And then we look at sole source, I totally agree, Sanaz, we look more towards either in a broad suite of crops, we will tend to look less towards necessarily like a narrow band or a heavy red 660 focus spectra. We're much more aware of the needs that crops have in sole source environments to have a more representative or broad spectrum component in some cases, especially if we start looking at crops like pepper and ones that need that extension growth and won't get it with a more narrow band spectrum. But always we're trying to find that sweet spot where the crop outcomes are achieved on the yield basis and the quality basis, and that we've maximized the electrical efficiency of that operation.
That's great. Thank you all for the comprehensive discussion. Erica, do you want to take the next question?
Sure. Yeah, thanks everybody. And I think it's a good segue. We talk about spectrum and intensity. So the second question that I got from the people registering for this roundtable was, what is the best way to measure greenhouse lighting? And we can say maybe CEA lighting, we can use for indoor farms as well. A few points to consider here would be, if you have any thoughts on the new discussion of PAR, that goes from 400 to 700 nanometers to EPAR. Now there are conversations about including the far red and measuring, being part of the photosynthetic active radiation to be measured in terms of quantum efficiency. And also few specific points when you think about using the sensor itself. So for example, the measurement frequency, how often you'll be sampling the light intensity inside your greenhouse, spatial resolution, so how many sensors would you need, and sensor placement location. So for example, outside the greenhouse, inside the greenhouse, where inside the greenhouse, under the lights, above the lights, and so on. So let's kick this question for discussion. I will go over my screen order. I think it's different from the other. So I start with Woodsmith, sorry.
Sure. Like I was talking about previously, one of the big things that we do is to use sensors at 5 different frequencies, which are pretty much tied into the photosynthetic frequencies. So the ideal behind that is in open greenhouse where you do have natural lighting. We can look at the natural light contribution to the overall light levels versus what is optimum for plant growth, and basically dynamically adjust that. So about every second we update the difference between the sensors and what we are looking for in terms of spectrum of light and intensity of light, and adjust correspondingly. Like I said earlier, that varies over the course of the day. So, the spectrum of lighting, natural lighting, changes all over the course of the day, and we can compensate that accordingly. It does also depend upon what stage the plant is in its growth cycles. There's going to be certain spectra that are optimized for seedling stage as opposed to vegetative growth and fruit production. So all of that gets built into the program, and over the course of time between what the sensors see, the natural light contribution, and what is optimum for the plant growth, the system just constantly updates it. That's been the most efficient approach that we've found to this point. Location of the sensors, they need to see what the plant sees. So obviously it's best to place the sensors in a location that emulates what the plant's going to actually see. And then that gives us the ability to come back and do a spectrum adjustment pretty much continuously. Like I said, we update about every second. So it's a lot of data, but it works well. All right. I think that pretty much said what I wanted to say.
Perfect. Thanks, Woody. Brian, if you want to comment.
Yeah, so to break it down into kind of the points you talked about, I mean, with EPAR being sort of evaluated now, we feel like that's definitely something that warrants being measured, because the impact is, you know, it really does make a difference for certain crops. And so we need to understand what's there. If that light is being used by the plants, we want to make sure that we include that into the measurement to get the most accurate representation of what, you know, the plants are receiving, what the lights are giving, and what the natural daylight is providing as well. When we look at, you know, sensor placement, choosing sensors, things like that, again, this varies depending on the crops. With a lettuce crop, you know, measuring crop height in the middle of the greenhouse is going to be most likely sufficient. With a vine crop, you know, having sensors at the head and at the base, and then again measuring outside the greenhouse as well to understand what the natural daylight may be producing, or at least within the greenhouse above the lights, or in a situation where it's not being impacted by the lights, to understand what the crop's getting makes sense. And so obviously it's one of those things that comes down to the more sensors you can afford to put in your greenhouse, the better, basically. And the more control you have by monitoring those over extended periods of time, the better. You know, for small scale growers, that may be walking around with a PAR sensor in your hand and looking at what's happening. For you know, full commercial scale growers, then obviously you're going to have environmental monitoring systems that are going to be using this data to control your lights potentially. So it really comes down to what your scale is. You know, the main thing is to understand, you know, what your crop's getting, and try to understand that how it relates to DLI. And, you know, that's the key thing that we're trying to keep up with, is make sure that the plants are getting sufficient light, and whether we need to supplement that with artificial lighting.
Perfect. Thanks, Brian. And just before I go, Luis, you're the next one. Just before I go to you, just a clarification. I don't know if I was. So for PAR, we define PAR as photosynthetic active radiation that goes from 4 to 700 nanometers. That's a widely used metric. And now there is new suggestions and discussions for EPAR, which is the extended photosynthetic active radiation, being proposed to go from 400 to 750 nanometers, including the far red photos. I just want to bring this to the audience in case not everybody is aware of that. And I put some information on the chat here for more supplemental information. Luis, let's go with you now. Luis from Sollum.
Thank you, Erico. So I think we're pretty much on the same page here. EPAR definitely is the way to measure, you know, the importance of far red being demonstrated in many case studies. And also with respect to the sensors, I would be with Woody and Brian. You know, the more data you have, you know, the better it is. You know, at the top of the canopy, so you can measure exactly what the crop gets. And the placement is also important. You need to have multiple touch points so that you can also like observe shadow effects that can happen during the day, or cloud movements, depending on the size of your facility. And I would say that your selection and your decision that will be made on that front depend also on, you know, the capability of your lighting system. You know, if it's just one grid that goes up and down, you may not need to have too much details. If you have something very granular that by zones can have like dynamic dimming and spectrum adjustment, so that your whole greenhouse, whatever is happening, has a truly like stable intensity and spectrum to the crop, will have definitely a big impact. So, but on our side, we really favor having the most data. We even share data with other systems. You probably have a climate management system there, so that we're going to get the data from there, from the top of the greenhouse canopy. And it's bringing all that together that truly brings the insights that are needed to make proper decisions, so that you get the ultimate light at each stage of growth, and for the quality of your crop and your yield.
Perfect. Thanks, Luis. Colin, you're next.
Sure, just unmute myself. So when it comes to PAR and EPAR, there's a lot of interest in both, especially moving towards EPAR as of late, especially as more and more luminaires start to incorporate far red into the artificial spectrum that they emit. But for the current time being, as it stands, for measuring light quantity and trying to establish a DLI or a total light sum, we stick to and would recommend any non-academic application to stick to a PAR value. It's already well established in both academics and in practice across an abundance of species with reproducible expected results when it comes to manufacturer estimates and resultant crop performances. It's easier to parse through a proprietary data set, I guess I should say, when it comes to measuring on an equal measuring stick like PAR. What we're seeing is that there is not only species, but a cultivar response in the likelihood or the propensity of a plant to additively produce more yield as you increase the total light sum with additions of far red. So we're not convinced that it will move into commercial measurement practice. And until the ASABI guidelines, which we are still working in adherence to through the like DLC certification standards, until those change, I would imagine we'd be apprehensive to move into it. So we're still looking at it on a selective extension, crop extension based, or like physiological secondary response is what we still look at in terms of the addition of far red. But in terms of measuring it, it is interesting to look at, say, that sunset response that was mentioned earlier. That's something we heavily see come up and would recommend in several crop applications. But to see on site what that spectral change that takes place during those events, especially if that grower is utilizing those events to achieve some outcome in their crop, I think that is of really high interest, even in our applications today. But for me, getting more certainty around what responses we could expect by each crop species is still needed before we start to look at it on a quantitative light sum basis. But in general, in practice, when it comes to measurement frequency, spatial resolution, and the sensor placement locations, would recommend at least one sensor outside and inside the greenhouse to derive a more accurate light transmission percentage than would be estimated by the material's age and type. That way you can have a more accurate assessment of what's getting through the greenhouse, so you can know when to either clean or apply whitewash, as well as having at least one sensor at crop level and one per control area if you're going to be switching different circuits on and off, or dimming with different buildings, maybe have different orientation, and always making sure that sensor is placed in a representative average location, or if multiples are used, that you derive what is close to an average. Sorry if that was too long, but I tried to hit all those points.
No, that was very nice. Thanks, Colin. Last but not least, Sanas.
Sure. So I agree with the points that were made. What I want to add is that, yeah, so I have been in greenhouses that the light compared to outside is like over 60-70% lowered because it's not maybe clean, or the material that is used for the glass or the cover is in a way that is just reducing the sunlight by a lot. So we need to consider that when we want to know how much light the plant is receiving. We're basically measuring the number of photons that are reaching this plant level. So it's important we measure at that level to know how much light we're providing. In case of providing supplemental light, so we are in a greenhouse, we have sunlight, and we want to provide supplemental light. It is important to have sensors inside the greenhouse, and ideally in different zones, because the sun is moving throughout the day, and depending on the orientation of the greenhouse, this is the light that each part of the greenhouse is receiving can be different. So this will be really helpful to define zones and to maintain the light by measuring the light that we are receiving from the sun throughout the day in each and every zone, and change the supplemental lighting based on that.
Perfect. Thanks, Anas.
Mhm.
Next question now, I'm gonna go with Neil. Back to Neil.
Yeah, thank you, Erico. So my question relates more to if you look at lighting different crops, and we know that crops have different responses to light. Some have higher requirements, some have lower. Do you have kind of metrics that you look at? Are there, for example, for a crop, maybe like per extra mole that you add, you get an extra gram of biomass? Or do you have kind of equations or metrics like that? Or do you have kind of groupings of crops into like daily light integral requirements? But basically, what helps you work with a grower to decide on what lighting installation intensity or target makes sense for the crop that they have? And let's see, maybe I'll go to Brian first.
All right, so when we start looking at, yield per light, definitely different crops require different DLI. And that's the first place we need to start, is understanding what the expected crops that are going to be grown. We have to look at the region that those crops are growing in to determine what that annual DLI in that particular area is, or the daily DLI as it gets divided out over that year. According to the lowest month, typically in North America, December, January timeframe. If we look at the lowest light levels, and then we start working kind of from there to try to determine how much light we need to keep that crop growing efficiently during those low light periods. So if we're in Texas and we've got a pretty good winter light, we may not only need 125 micromoles to supplement and get the DLI that we need for a lettuce, leafy greens type crop to continue to thrive, even in the winter months. We also want to look at, how much we're pulling shade in the summertime, because a lot of times in Texas specifically, or southern climates, Florida, places like that, it may be more energy efficient to pull shade and run your LED lights versus trying to utilize that natural sunlight and having to cool the greenhouse and deal with the environmental conditions there. It all comes down to those 9 different variables that we have to control. So as we increase light, are we going past what that plant's ability to use light is? Are we exceeding the DLI that crop would need? Or are we pushing the plant into a growth phase that we're not able to keep up with other variables, supplemental CO2, things of that nature, to make that crop flourish? And so those all have to be taken into consideration when we look at how much light we're providing. And then it comes down to, cost effectiveness. And this is where we have to be very careful that 1 gram of, or 1% of light increases 1% of yield. There's a cost effectiveness there, that where do we draw the line between that capital expense to get more light and the operational expense of running those lights? And then how efficient are the lights in general? So obviously the industry is going towards 3, 3.2, 3.5, 3.6 micromoles per joule efficiency. So we're getting very efficient fixtures. But where do we draw the line of incremental gains on those fixtures to add more light at more efficiency if it costs so much that the growers can't afford to buy those fixtures in the end? And so LEDs are maturing to a point where I feel like there's not going to be a lot of gains in that efficiency side of things. But we're going to start looking at how can we reduce that CapEx so we can get those lights into a greenhouse more efficiently and in a more cost-effective manner. Then we look at, again, crop type, value of the crop. If we're looking at a cannabis crop, obviously, the more light, the more yield, the more value there. If we're doing things like supplemental CO2 and crop steering and things to continue to address the needs of the plant. But when we look at leafy greens, there's going to be a theoretical maximum that's not cost effective if we go beyond that. And so that's what we try to look at. It's more based on, what the goal of the grower is. Is it, we want to put more light and do this in the most advanced way we can and try to take advantage of that? Or are we trying to be more cost efficient and just use sunlight and supplement where we need to keep those crops going? And I think it's very dependent on the situation.
Thank you. Brian, a follow-up question came up. I'll have you check the Q&A and respond to that one. And then I'll toss the question over to Colin next and let him respond.
Thanks, Neil. Yeah, when I saw this question, my eyes really lit up. So this is the bread and butter of what I do as a job, 40 hours a week, is try to collect and monitor in practice the constantly evolving light use efficiencies in practice methods of our growers in North America. And what we see is grams per mole. It's a very powerful metric in terms of how many grams of final saleable product did you produce per quantifiable mole of light. So it's just a relative measurement of how effectively the plants use that light. And we call it light use efficiency, or LUE, in our internal circles as plant specialists. And we see that it ranges widely by crop, not only between different crops, but within a given species. Like for instance, lettuce, if you look at a 400-gram Belgian butterhead grower, it'll be around 20 grams per mole. So that once that plant gets to that large size, its leaf area index increases such that its light interception capabilities are exponentially also increasing. So its light capturing and conversion ability is highest at the end of the cycle. And when we come to North America, we have more of trends towards higher light intensities. We see more and more interest in that, but there's, like Brian said, really got to make sure you don't exceed that tipping point on the photosynthetic curve, where every dollar spent on running those lights, every kilowatt hour you pay for, actually exceeds the added yield that you would result in. So a lot of what we're trying to do is parse out these individual application characteristics or parameters. So what's the crop cultivar? What's the mature weight? What's the time to harvest? All these factors directly influence the light use efficiency. And so when we approach a project, it's always a case-by-case basis. Much like I learned in college, you Google the academic literature, then you look at the vast, pool of commercial practice data that we have, and then we continuously try to push that ball forward and set up new projects so that we can continue to stay 1 or 2 steps ahead of these trends. And higher light intensities over low maturity lettuce crops is more and more interest. And so that to me is of the highest focus in what I do in terms of the crop spread, but definitely a really fascinating field to learn more about. It sounds very heady scientific, grams per mole, but at the end of the day, it's a really important metric tying to the overall efficiency of the production method itself.
Thank you, Colin. Sanaz, do you want to take a crack at it?
Yeah, absolutely. So I think when we're looking at this cost, when we're talking about cost, we need to look at the entire production cost that includes lighting, labor, like everything that goes into this grow. It's important to look at it from this perspective, like the cost of energy, and we need to consider that cost of energy is different country by country, even state by state, region by region. So these are the things that will affect if we look at it as like the whole production cost. And something that was mentioned is that light intensity, we touched upon it. I feel like we are comfortable by increasing the light intensity in cannabis or hemp. We know that we will get better yields with that. And so we're comfortable with doing that, with pushing the plants, but not so with leafy greens. But what I'm seeing is that people like lettuce growers are getting a little bit, comfortable with doing that. And I have heard that like a company is growing lettuce at 800 ppfd, which is not, which is definitely higher than the what is recommended out there. But I really believe that we need to push the plants. They will be able to take it, but we need to provide all the like the optimum environment for the plant, because when we are pushing them, we are this metabolism is faster. So we need to provide everything else that it's nutrients, CO2, and everything else for the plant to be able to grow better and do a better job. And consequently, we get a better, more biomass and more biomass per 1 mole of light that we are providing there.
Thank you, Sanaz. Woody, can I ask this question to you? And then there was also something that came up in the Q&A, which is, as we know, the CO2 concentration affects the plant's ability to use light as well. So should we also factor into these lighting targets or lighting equations, the carbon dioxide concentration too?
Sure. Yes, all the above. We produced this thing because early on we got into situations dealing with cannabis growers and a bunch of other people about, okay, well, if I just adjust the light level, what's going to happen? And it is a much more complex consideration than just that. Pushing the light levels is one thing, but what's the spectrum of lighting? Also CO2 levels, nutrient delivery, temperature, humidity, all these things come into play. And it's a fairly important thing. So we developed this little thing we call an incubator, which is basically a little 1 meter cube that you can stick a plant inside. And we're supplying these to several universities now. Punjab Agricultural University in India has got 11 of these things. And what they do is basically stick identical plants in all 11 of the incubators, and then they can vary the parameters. So they can vary CO2 levels, temperature, humidity, lighting intensity, spectrum of lighting, and duration of lighting. Because we also find out a lot of plants will grow better with extended duration. Some don't like it. Some plants need a very specific rest period for the plant to catch up. So, it is a much more complicated question than just changing the light level changes everything. The point being that things like CO2 levels, temperature, humidity, frequency of watering, dampness of the root. We do moisture sensors at the roots to determine just how wet or dry the root is. We have one customer that's growing saffron, and saffron requires a very well-drained environment. So it has to be put into either sand or vermiculite, something like that. And it requires a big temperature swing, being grown typically in the deserts and northern parts of India. We try to emulate those conditions so that we know what all these different contributing factors are. And then we can come back and look at what is the optimum lighting intensity and lighting spectrum. And again, that will change over the plant's growth cycle. It's very different early on at seedling stage than it is when you're trying to push vegetative growth, then into the flowering stages and ultimately fruit production. So, that's kind of what we had to do to really try and get a grip on what really is going on with a plant beyond just how bright is it and how many hours a day do you light it. So yes, it's a much more complex situation and takes a lot more analysis of all the different conditions to really determine what's optimum. Okay.
Thank you. Yeah, all those interacting factors, they're like job security for a plant physiologist like myself.
Absolutely.
There you go. Good. And then Lewis.
Yes. Well, yeah, I think that is the key question. When you look at the economic models and the return on investment for a lighting solution, yield productivity has the biggest weight on the whole investment, even more than efficacy and power consumption. So it's critical that the system is well dimensioned. So it was mentioned that you make sure you have the right dimensioning for your darkest months of the year, which in the Northern Hemisphere obviously happen in December and January. But then also on and on, It's for the grower needs to have an environment he can control so that he can adapt to the changes in the market. You know, if the demand for its produce is going down, he may want just to slow it down, because even though he's going to have yield, like he won't be able to, he won't get the price he wants for it. So these are all aspects. So bringing back to the crop, you know, we also see it's an extension of the light saturation concept. So you know, at some point, you know, the plant has reached a saturation level. It has received enough of red or enough of blue. So adding more, yes, brings more yield, but it's all a matter of balancing, you know, everything together. And it becomes more a challenge as you get more to the northern part of the US and then in Canada, where, you know, obviously supplemental lighting plays a big role in winter, and the systems is used way more than it's going to be like in Texas. So, but again, at the end, it comes to the overall cost of production, and then the effect on the light on nutrient uptakes, also that should be noted. So, and it's all, which all makes it together, like the economics and the return on investment for the grower.
Thank you. Great. And we're quickly running out of time, but Haley might do a rapid fire next question.
I have a final question. You each get 1 minute. So, what are your customers asking for when it comes to lights? Are there any new LED developments that have come out that are based on grower needs? Are there any new crops coming up that are requiring supplemental lighting? Just, yeah, what's the impression that you're getting from your grower customers right now, and how are you working to address it? And let's start with Sollum. Louis.
Well, on our side, you know, what is interesting is Sollum provides a programmable dynamic lighting solution. So, you know, the type of requests we receive from customers is they want us to enrich our library so that we provide them with more different type of light recipes and lighting protocols so that they can play with it, because they rapidly see the impact as they can play with it, as they adapt lighting and intensity and spectrum at each stage of growth, enabling them to get like better crop. We're actually enabling the grower to even do what he's been doing for decades and be a better grower by controlling the light. So we see them having more control in the spectrum, defining zones, and some zone they're asking us to partner with bio companies so that we can also have lighting protocols to manage pest infestation. So it's truly in that direction that we see a lot of the requirements coming from the grower. More flexibility, more sophistication, so that they have a much better control in all aspects of the greenhouse.
Sorry, I was muted. Next, Sanaz. Thank you, Louis.
Sure, I will just give a very quick and short answer. So something that our customers want is success stories. They really want to see lighting in action and how successful the grows are. This is really important for them. And also, you know, they want support after they have the lights. But we know that growing practices, the recipes are really important. You know, we touched upon like CO2 requirements. When more light, CO2 need is also going higher. And it's the same for other factors as well. And this is really important to provide this consult to people, to growers.
Great, thank you. Next, Woody.
When we talk to a lot of the end users, a lot of them are still looking at fluorescence or metal halide or high pressure sodium, stuff like that. But as we go through the details of what needs to be done, the only thing that makes any sense is the LED solution right now, because you've got control of spectrum, you've got dimming capabilities, you have the ability to alter intensity and change spectrum over time, things like that. So, you know, when we really can get with a customer and go through an explanation of what's really going on and what the plant needs to optimize its growth, the only solution that's viable for us is an LED solution. And we've been very successful in convincing customers that that's really the way to do it at this point.
All right, thank you. Colin?
Sure. So we get a lot of questions. The first one I always hear is more data. They always new innovations and new application methods spur the need for new data. And so for me, one of the biggest things I try to do is improve the data collection practices that we have as a team, so we can constantly keep a pulse on how these applications are moving, because they move quick. Well, one of the slower trends, but it's sort of unidirectional, and I don't expect it'll quit anytime soon, is the trend towards more efficient products. And not in just the running cost or the operational cost in terms of kilowatt hours, which can often be one of the, if not the leading production expense in a facility, even in a greenhouse, especially in a city farm, is the rebate. The rebate can be heavily affected on an upfront cost of the installation based on the efficacy of a module. So you'll have a utility who's incentivizing basically a retrofit of what would be a legacy product type like HPS or CMH. They're basically able to net out their savings on being able to sell that electricity you won't use into the municipal or higher margin marketplace. And so a lot of customers we see getting rebates typically between 10 to 40% is your typical range, but we've seen some projects in Canada and California actually be 90% or in some cases actually completely covered. So that's a huge focus from our customers is, how can we make the most out of what we spend on an operational cost basis? So how do we get more efficient greenhouse spectra? How do we get more efficient indoor spectra? And then how do we make the most of the rebate packages as well? And then some of the other features that are always being asked about, like dimming. There's always questions about spectral impacts and the difference between blue fractions. And so, but those first two I listed are definitely the ones that dominate the conversation.
Great. And Brian?
Yeah, so kind of to parrot what everybody else has said, energy efficiency is one of the things that people are looking for right now. Really trying to improve on what the HPS fixtures and the legacy fixtures were doing, and even to look at, how current LEDs are more energy efficient than they were just a few years ago. And so, that's one of the big things we're looking at. We're seeing some interest in higher output fixtures, which can reduce some of the other costs for installation and maintenance and things of that nature. But one of the big things we get, asked about a lot is research. We work with a lot of different universities to try to understand how the different spectrums and far red and all these developments are coming out. And so customers want to know confidently that the spectrums they're choosing, the light intensities they're choosing, are research backed, and that they are going to make measurable impact on their crop. And so that's something we get asked a lot. And then obviously rebates. It's a huge thing right now with LEDs replacing HPS, the power grid, trying to support that. And so being able to show, help a customer get rebates is something that as a service we offer a lot. And lastly, for our products, a lot of people are looking for products made in North America. And so we have production in North America, and that's something with global supply chain issues. Having a domestic supplier has been really important for a lot of our customers.
Good point. All right, we are at the top of the hour. Thank you so much to all of our panelists. That was a really amazing discussion. Some really good points brought up, and thank you to all of our registrants for joining. And the recording will be up next week.
Thank you.
Have a good day.
Thank you
Enjoyed
so
it.
much.
Bye.
Thank you very much.
Have a good day,
Bye.
everyone.